Okay, record is on. So where is, okay, so our task is at the same location as chat. Where is the chat? Here is chat. It is here, so it is here. This one, the same location as for this task, yes, same document, but we go next to the next task. This one is our new scheme, where our task is to calculate relay protection, distance protection for serious relays. For example, let's take the first variant, this one, for A and E. So this relay protection and this one. To simplify this task, let's separate this into 4 steps, 4 main steps. So approximately 1 week per each step. So in 4 weeks, I think you could deal with this task. I have to say, if you do your best. So let's start with the first step. We need to calculate short circuit currents for A and E relays. At the beginning, at the first iteration, we need to calculate the fault current, of course, and voltage when the fault is on the bus 2 and the fault is on the bus 3. So relay A protects line 1, so the fault is on the bus number 2 to be sure that the A relay, the protection is directed protection, so it protect the line number 1. So to be sure that it's feasible to protect line number 1, so we check how this relay will be sensitive if the fault will appear on the bus number 2. And the same situation for the E relay for line number 2. So that's why the fault will be located on the bus 3. Okay, so how we could calculate current value. So you have 2 options. First of all, you could use everything you know to build this network and to calculate the fault values. This is the first option. The second option is to use this ready-made MATLAB program. There are 2 parts of this program. First of all, this is a program number 4, and this is a Zeidel function for this program to calculate. This is the Zeidel method, the Zeidel approach, Zeidel approach, yes. To solve, this is the math solver, yeah, to solve, how to say, the task for this code, for this program. Let's go to see what we got here. So here we got the code here and here. Yes, so you should save this one like a file, yeah, .m MATLAB file. And this one, the same MATLAB file, the only you should know that this function should be in the same folder as the main code, because the MATLAB as a default will search this when we call here the function. MATLAB looks for this function into the map where this file is located. So you should place these 2 files into one map. So, okay, this is a MATLAB code. What we see here, first of all, here we have the first group with input data. So this is line length. This is line impedance, yeah, active reactive for 1 kilometer. input data. This is the power of a transformer. Yes, T transformer power. Yeah, you see it is multiplied in, because to be sure that every unit is correct, that's why we use these volt amps, not kilo, yeah, not mega, just real values. That's why we multiply these 25 megavolt amps, not to use mega. This is a generator power. This is EDS, because we represent each generator with EDS source, yeah. This is the generator impedance, transformer impedance here, yeah, line impedance. So this, all of this is input data. This is all input data. Of course, this is a sample, yeah. All the values, all the data, because you could have different number of lines, yes, different number of generators and transformers. This is just a sample, yeah. So you should change everything you need for your calculation. So this is, okay, this is input data. What is important here? Here we have two types of impedance. Positive sequence impedance and negative sequence impedance. We should remember that they have different impedance. But this is about the input data. To be easier, you could use this one. No, sorry, I'm wrong. This one, this number 3. Yeah. Pictures from this document, because this document is in Latvian, it's not very useful, but it contains the main thing you should know about how to represent the network with positive, negative, and zero sequence. This is the sample. This scheme is very similar to the scheme of your homework, because here we have 3 lines, the same as in your homework. The main difference here is a system and here is a system. But in your homework, we have 2 generators and 1 system, yeah? So very, very close to, where is it? Where is it? Yeah, okay, yes. Very close to this one. And to calculate the fault values, first of all, you need to represent this network. You should build this scheme using the resistance, electromotive force, and so on. All 3 sequences. So to be more easier, you could find in the internet information about this symmetric component theory and make a look about how it works, because I described this theory very short to you previous, just for information, you know. But as you decided to try to calculate this task, so you need to go more deep in this theory. So what we got here? Here we got 3 sequences. This one is positive sequence, this one is negative sequence, and this one is zero sequence. Here we go. And these nodes, node number 2, 5, and this one, yeah, where we got the fault. So here is this network, and this fault, like it is shown in this picture, is represented here as well. So this fault is somewhere into a line. That's why we divide line into 2 parts: the resistance before the fault and the resistance after the fault. This is quite good option, because, for example, if we need to make the fault on the bus, like here, yeah, we just can change the impedance of these 2 elements without changing the network, yeah? So the scheme. We just say that this resistance is 0.99% of the full line resistance, and this is 0.001% of the line resistance. And in this case, it means that we can move this resistance where we want, or this fault where we want, and without any change in this schematic, only changing the value of impedances. Yes, this is quite easier. So using this, you could make free metrics for the calculation. Why we need to do this? Because this scheme is a representative of this, and only using this theory and this scheme we could calculate the values of current and voltages. But this scheme is quite complicated, and to calculate it manually, it's not good. That's why we use a machine to do this work. But for machine, we need to provide the information, the topology of this scheme, where are the sources, and so on. That's why we represent this scheme using the metrics form. So, how we build this representative network? So we replace each generator or a system with an EMS, electric motive force. So this is electric motive force. This is a system, so the system does not have an resistance. That's why we don't have a resistance of a system here. But if we have a generator, yeah, it means that it has a resistance impedance. Yeah, so we need to put together to the electromotive force the resistance of this generator. Next one is the transformer resistance. Here you could see it's only reactive resistance. It's quite enough because active resistance is small and we could cut it. Next one is the Z, the full resistance of each line. Yeah. And this, the natural wire. First, positive sequence is here. Next, we must choose the direction of current in each branch. We could choose it very briefly, so whatever we want, because the program result will show us is our direction right or wrong. If we got the positive current value, it means that the direction is right. If we got the negative values, it means the real direction is opposite. Okay, and we need to get the name for each node. But there is one very important thing, that all the nodes, yes, of the scheme are represented with a number except one node. The last node which is connected to the natural wire, this one, yeah, this one does not have a number because it's a base node and its voltage is equal to 0. That's why it is not represented with the number. It will not be represented in the matrix. So we build this scheme, and after that we need to fill three matrices. The first matrix is M. Here we got all the branches from 1 to 17 as it is here. Yes, you could see the first two, and the last one is this one, 17th. And here we got the nodes from 1 to 9, from 1 to 9. Yeah, so the total number is 10, but as I said, one is missing because its voltage is equal to 0. And how we fill this matrix. So if a branch is connected to the node and this current flows into the node, we write -1. If the current flows from the node, we write plus 1. If there is no any connection, we write 0. For example, this one is the first node, branch number 1. First node, branch number 1, current is flowing into the node. We write -1. Here we go. Branch number 2, where it is? It is here. There is no any connection with the node number 1, so we write 0. Branch number 3, it flows from the node number 1. We write 1 plus 1. This is the way how we fill this M matrix. The second one is the branch matrix or the resistance matrix. So we have 17 branches, and we need to write here every branch resistance here. And this is the electromotive force matrix, where we go the column matrix, 17 branches, and we write if there is an electromotive force in this branch, we write its value. If there is no electromotive force, we write 0. So in this case, the first step is for this network, to make this representative scheme when you got the fault into the line number 1. This is the first scheme. And the second one is when you got the fault into the line number 2. After that, you need to write this M matrix, this electromotive force column matrix, and this the branch impedance matrix for every scheme, and where is it? No. Where is it? Okay, and to put this information to the code. Here you go, this M matrix, this is electromotive force matrix, and this is the branch resistance matrix. To put this into the code. So this is the first step. What you should do. And this program, when you fill everything you need, you will get the result. What you will get the result? You will get, okay, there is some words. You will get the values of each current for every current in every branch. You will get the matrix with currents and the matrix with voltage. So you will know the voltage in every node and the current in every branch. Knowing this, you could calculate the phase current and the phase voltage, what the protection will see in the case of fault. And this is the input data for set point calculation. Maybe any questions for the first step?